All right. Atomic theory. We go way back, BC. We go and we get to Democritus. And Democritus said that the atom is the smallest piece of matter, and never tried to do anything. They didn't have anything that they could even try it with, cutting it, and he wouldn't try it anyway, because the Greeks, like I said, didn't do anything. They just thought it through, and he said if you just keep cutting things, eventually you'd get to a piece that was so small you couldn't cut it in half anymore. It would be the basic building block. And he said that smallest piece was atomos, or the smallest piece of it means discontinuous. The guy in the video said uncuttable. And he said that that's what we're going to say is a building block. And his reason was there had to be an end. No reason for calling it a sphere, but a sphere seems to be the perfect shape, geometric shape, 3D, because it has, for the surface area, it has the largest volume per surface area. So he just assumed that it would be a sphere. And I don't know how much we actually know about what he looks like, but I like this better than the picture that they give to him in the book that has that one little Charlie Brown curl in the front. He looks wiser in this particular toga. This was what we had for quite a while, and they divided everything into 4 elements, and you've heard it before: earth, wind, fire, and water, and everything was made out of those. Rocks were made out of earth. Plants had earth and water and air. They knew you needed all of those in those. People had all of those because we eat the plants, but we also had fire, because that's what keeps us warm. And when somebody dies, then they go to room temperature because their fire went out. Luckily, they didn't do any experiments. They didn't go in and start looking for people's fire. But there had to be something that kept them warm. They didn't have any idea of the whole enthalpy, where a chemical reaction gives off heat. It's exothermic, and that's what keeps us warm. They're just, the only thing that provided heat was some kind of fire. So that was actually the basis for chemistry for a long, long time. Not quite till what the next person is, but it was for probably a millennia. That's pretty much all they had. John Dalton was an English school teacher, and he used experiments. He was very different than the Greek. Everything had to be tried. He still said, he came to the same conclusion: the atom is an indestructible sphere. That was left over from what Democritus said. But he said each element has its own properties, and they combine in definite patterns. So when you make Kool-Aid, little package. Did you know where Kool-Aid was invented? Hastings, Nebraska. There's a museum there, and you can go to the Kool-Aid display, and you can make your old, where they first came out, you can print your own Kool-Aid package, whatever, and they have all the commercials from all the way back to when they began advertising on TV, and you can watch the decades worth of commercials. It's kind of fun. But when you make Kool-Aid, you get one package, and they used to be little envelopes. Now they come in these little tubes or whatever, but back when I was a kid, and they were these little packages. In each package, you put into 2 quarts of water, 2 quarts of water, half a gallon, and it gets a cup of sugar. And that's what the package says. But you don't have to do it that way. My wife, when the kids were little, thought that's more sugar than they need, so she would put half a cup of sugar in, and it was still Kool-Aid. It actually quenched your thirst a little bit. It wasn't as satisfying, but it was still Kool-Aid. My son thought if 1 cup is good, 2 cups will be better. When he made it, his was kind of crunchy Kool-Aid, and it was very sweet. Did not quench your thirst at all, but he loved the flavor of the really sweet. But it was always Kool-Aid, and you can do that when we cook. You can't do that, according to John Dalton, he's correct, with the way atoms combine. So a simple example is if we make water, it's 2 hydrogens and 1 oxygen. Hydrogen is super small, so if we change it just a little bit, it shouldn't make much of a difference. So instead of 2 of them, let's say we give 3 of them. Well, that actually makes it, you added an extra proton to it. It makes it a positive. It's an H3O. We haven't got there yet, but it's coming. Ion. It's actually a hydronium ion, and that's what makes an acid. So at that point, this is refreshing, necessary for life. Depending on how concentrate this is, it could kill you. It could burn all the way down. One of those things where they say do not induce vomiting, because it will burn all the way down and it'll burn all the way back up again. So that does not equal that. That one's no good. So what if we, instead of adding, we just take 1 away? It's actually usually rewritten the other direction, and we took a hydrogen away. If adding 1 makes it a plus, take it away, it'll make it a minus. And that's a hydroxide ion, key part of drain cleaner. So again, refreshing in a bottle of Drano or liquid plumber, not as refreshing. Same thing. You drink it, don't induce vomiting, because it will burn all the way down, it will burn all the way back up. Not as good. What if we add an extra oxygen? This you're familiar with. That's hydrogen peroxide. And the little brown bottle that you get that's in your bathroom that your mom tells you, that little fib that when I pour this on the cut, it's not going to hurt at all. It stings a little bit, but it's worth it because you're going to see a bubble and everything. But that's just a 3% solution. That's 97% water and just a drop or 2 of hydrogen peroxide. When I buy it at 30%, and if that just a little bit as you're pouring, if it a little bit spills on wherever it does, it completely bleaches out, and it's just white, like the whiteboard on there, bleaches all the skin out, and it burns a little bit. So hydrogen peroxide, my mom made me gargle with it if I had a sore throat. That was 3% poured into water, so made it even less, probably 1% or less than that. And it still had quite a, it was not refreshing, but it would not be good to that. There is only one way to make water. It has to be 2 parts hydrogen, 1 part oxygen, which makes the rest of chemistry easier to understand. It does let us do math on it, but some people don't like that. But he is correct that there is the law of definite composition. They always combine the same way. And there were 5 things, and I think I saw in there that you wrote all of them down. That's fine. The part that we're going to use is that each element has its own unique properties, because we're going to eventually build what an atom is and the periodic table. So each one has its own properties, but the others are fine. You can leave them on there, but that's the one that you can put a star beside one or whatever. That's the one to remember. But his model, some of the science behind it is different, but he still has the same model that Democritus had. So we're 2,000 years later, he's in the 1800s, and we still have the same model. The next guy, J.J. Thomson, added electrical charges to the atom, and different time, and I don't know if they always, if this was just for a picture, if they always dressed up like this to work in a lab. And you can actually see the picture. This is his cathode ray tube that he was working on. And the rest of the picture, it's a fairly famous picture, has the wires going into a bunch of jars that have electrodes in it. It was very crude, the first type of battery that they could use, chemical battery that he's using. But his findings were pretty interesting. Well, actually, and we will try and, I'm going to give you some tape. I'm going to show you a very quick way to do this. It's not going to be as satisfying to them. Let me turn this around. Onto your table. We go down. There we go. Whoops. That'll be good for now. We'll put some tape on here. Need another one. The folded over part is just a handle so you can get it off. No magic there. Okay. Now I want you to, I want you to take the handles, and you can do it one at a time, but rip it up very quickly. Yep. Now do the same thing to the other, but no, with the other hand. Yeah. Ambidextrous. There you go. That's all right. Okay. Now don't let them touch. Try not to, but bring them close to each other. So they're faced, like that. And they're pushing away. Now he saw something that was similar to that. Now I'm going to change it up a little bit. And I'm going to put this on the table. And now take the bottom one and just rip it up really quick. Now take and quickly rip the two apart. Now, bring them close together. And now they go together. And that's similar to what, you don't have to do anything with them. They're done. We're finished with them. That's similar to what, oops, I need this here. You got JJ there? There we go. What J.J. Thomson found, and he actually did a very similar experiment to that, except he used glass rods and a thin sheet of rubber and fur. It was cat fur. I don't know where he got the cat fur, whether it was his, whether it was an annoying alley cat behind his lab or whatever, but cat fur, and he could make the rods, he had two of them, he could make them either go towards each other or away. The classic experiment they talked had to do with this cathode ray tube, which is this bottle right here that has electrodes on both sides. And he would shoot a charge of particles going through. Here is his battery. That's what batteries looked like back then. It's still the same thing that your car battery has. It has lead plates in here with acid down here, and the electrodes going in. It's much more portable than this. And he would shoot it, and normally it would just go straight across as it goes. And this is actually what led to a very, very early form of what eventually became a TV. Now, it was way after he did, but you have a bunch of these, and then you can focus them with what these cathodes, or these anodes here, just the negative. He had another battery over here, and he had a positive and negative charge, and he found that when he shot it through, instead of, it used to be going there, but now when he put the charges here, it gets deflected And if he did it the other way around, it would go up instead of down. It gets deflected away from the negative. So there was something on the outside that had the same charge, just like the two pieces of tape. When they had the same, when you did exactly the same thing to them, then it pushed them away. Something repels it and pushes it down. Now they can use that and they use different technology now, but the old great big TVs and the ones that, if you're going to watch something at 5 o'clock, you better turn the TV on at least 10 minutes early because all of the tubes had to warm up and stuff. But they would focus it with the different things here, and if they got messed up, then your picture wasn't clear. But he just found that there has to be something on the outside that has a charge, a negative charge. So he said there has to be something electrical there. So he said there's added the electrical charges to it, and he called the negative particles electrons. And he knew there had to be a positive part to the atom, but he didn't know what to call them. So he just left it in his model that there's a positive part that has on the outside these negative particles, and he called them electrons. Oops. Can I get rid of my dotted line? Go with us. So he called it the plum pudding model, and he said that these, and you can see they have a big plus sign here, he said that this pudding part was all positive, but then you can't really see it from there. Maybe you can see it better than I can because I'm so close. Well, you can kind of see that they have negative signs on all these plums that are there. These were the electrons, the negative electrons, and they're on the outside. Some people use the example now of chocolate chip cookie because we don't do plum pudding. And chocolate chip cookie works, except that it's two-dimensional, pretty much. It's flat. But if you took out chocolate chip cookie, especially right out of the oven, and you took a paper towel and rubbed on it, you get a little bit of cookie, but you'd mostly get that melted chocolate that was on there, and you get that on there, so you would discriminately get positive or negative charges. Either it's going to go from whatever material onto this atom or from this atom onto the material, depending on what the materials are. Now, the original plum pudding was actually a Christmas treat, and the guy from the video, he kind of drew it like, he was thinking that it's like pudding like we eat, like tapioca or chocolate or vanilla. Pudding in England is a cake, it's a bread, and students think, oh, we should make some of that. But I think the first ingredient, well, it might be flour. Second ingredient, I think, is beef lard. It's just flour with a lot of lard. And there's no plums in it. There are hard candies and some different kinds of nuts, hazelnuts, pecans, whatever they put in there. I don't know how it gets called plum pudding because everybody says it's not really, there's no plums. And what they would do is they would take, they'd often do it outside, and they'd take and make a fire, and they'd have a big pot that was boiling, and then they would put this, now this one obviously was in a bowl and it was baked, but the original ones they would tie up in like cheesecloth, tie a rope to it, and they would just take and lower that into the boiling water and let it cook. So flour and sugar, I'm sure, and beef fat in there till it all got nice and moist, and you had to have something that let it get hot, but you kept stuff in. Otherwise, you'd boil all of the sugar out of it. And you boil it too long, I'm sure you would. And the fat, it'd just be really dry, and it'd be a lump of like paste with your candies and pecans in there. So you have to boil it till it's just done, then take it out, unwrap it. Sometimes they would actually cook it in an oven, but it would still be in a fire. And then they go out, Christmas Carol, they do it that way. They cooked it in the oven along with the turkey, and it kind of gets flavored by the turkey as it cooks too. And then they set it in the snow for a while until the kinetic molecular model, the particles slow down, get closer together, and it shrinks a little bit, and then they can turn it out. Charles Dickens talks about turning out the plum pudding, and so you just flip it over, and then it'll just come right out of that, which makes sense because as it shrinks, there's also all that beef fat in there, so it's slippery, and it will come out. Not what we would eat. I've never had a class that said, yeah, that really sounds good when they see the recipe. But it does have a three-dimensional shape, and you can see on the outside there are these candies or the nuts or whatever that would act like the proton. So we still have this sphere, and it's no longer indestructible. There are different parts to it. You now have the positive pudding part, and you have a negative electron that you can take apart, which would give charges. Next guy, Ernest Rutherford. He also was in England, studied at Oxford, but is that what you put for nationality, English? Yeah. He's actually a Kiwi, which means he's from, that's what we're called Yankees, Canadians are called Canucks. He's from New Zealand. But it was a British colony, and so he studied. He went to school in England, and it makes sense. It would take forever to get information back and forth from New Zealand to England, whereas he's studying along with these other people, and he came up with his own idea, which is a fantastic idea. He's got this radioactive material that gives off alpha particles, which we now know is just a helium nucleus, 2 protons, 2 neutrons, and he wanted it focused, so he went through 2 lead plates here. This is also lead, symbol for, doesn't make any sense in English, but that's a symbol for lead. In Latin it's plumium, so then it does make sense, and it just has tiny, tiny slits, so each time it goes through less and less, it gets focused more and more. And then he had gold foil, which is just like aluminum foil that we use, except it's softer, so he could pound it, roll it flatter. He wanted to get as close to being 1 atom thick as he could, and then he shot these at it, and then he had this scintillating screen. Scintillation screen is how they call it, but it goes around here, and when the particles hit it, they react because they're electrically charged. When they hit it, it just lights up. It gives a little blip, but it's constant. There's so many billions and billions and billions of them hitting it that where it bounces off, it'll just continue lighting it. And the more that are hitting it, the brighter it will be. And most of them, as you can see, go straight through. Right here is the most there, but occasionally they get bounced off. Now, he was surprised more by the bouncing off because he had done some other experiments, and he had found that the mass was very, very small part of what the atom is, and this is his way of proving that. And so he said that there is, most of it is empty space, so it just goes right through, excuse me, without hitting anything. But occasionally it would hit something that is dense enough that it would actually make these particles bounce off. And so he used that to come up with, he changed his model, but he still had to keep what everybody else had said. Democritus still had part of it right, John Dalton, each one is different. J.J. Thomson, there has to be electrons, there's got to be a negative part. He just took, and he said that there's this really, and this is not to scale at all. If we had the nucleus this size, the electrons would probably be out on 680 somewhere. It would be that far away with that, but it doesn't work to have a model that's, because you wouldn't be able to see this size, you wouldn't be able to see the nucleus. But it's very, very tiny, and almost all of it, of the mass, is in this nucleus. This out here is pretty much empty space and no mass at all. But you, even at this, you can see that as you send something through, the chances of it, even at this, hitting anything are pretty small. But occasionally, they would have something come, and it would, and then it would get deflected off. And he said that this positive part, this is the positive part here, these are still the negative, just like J.J. Thomson had, and he called these the protons. It was made up of protons, so now we have the positives and the negatives canceling each other out. We have a neutral atom, but we have it broken up into different parts that have charges on it. James Chadwick didn't change his a whole lot, except that when he was actually able to measure it, they had mass spectrometers, and he said that there was too much weight. He knew that the electrons didn't have any of the weight, and he knew that the number of protons had to equal the number of electrons, so you couldn't have just a bunch more protons in it. He just said that, well, there has to be something else in there, a heavy particle in the nucleus, and he called them neutrons because they have to be neutral. They can't have a charge because the protons and electrons already balanced each other out. So we're going to add more mass, but not any charge. So he has these neutral particles that he added in to make the mass calculations come out correctly. So his model still looks just like what Rutherford's did. He just now has positive and neutral particles in the center. Then we get to the person of interest. Niels Bohr organized Rutherford's model into the solar system model. And we are going to figure out how he did that. Clock ends. And I will give you the lab that we are going to do, but you don't have to. You don't have to do anything. I mean, if you wanted to, you could. There's the background is just the first page. And then there are the checkup questions that are just, do you understand what's on that first page? So there's not a whole lot of it there that you're doing. And then it gives you the procedures that we're going to do. And I like this one. This one is good. It involves colored pencils and fire and so it's interesting and colorful, and there you can really see what Mr. Bohr was talking about. But we will do that on Monday.